Okay, so KSP is what we're going to be doing today, which is solubility equilibrium. So remember those solubility rules? When we tell you things are insoluble, it's actually kind of a lie. Okay, they are slightly soluble, and so that's what we're going to be doing now, is figuring out how much will actually dissolve. Okay, they still will form a precipitate when you mix them together in strong enough concentration, but a small amount actually does dissolve and become soluble. And so that's what this is going to be about, is calculating that. Okay, so we have slightly soluble salts. They do establish an equilibrium between being dissolved and being in a solid. So for instance, if we have silver chloride and in a solution of AgNO3, and we put the sodium chloride in there, you will get some that actually will dissolve a little bit. Okay, so that's what KSP is about, is seeing how much will dissolve. Okay, so remember that solids do not appear in the equilibrium expression, only aqueous and gases. So the good news about this is when you're doing the math, you'll never have anything on the bottom. Okay, because KSP is going to be equal to the two ions. Okay, because when you have the forward and reverse reaction of, for this instance, silver chloride, forward and backwards to making ions, you don't include the solid in there, so you just have KSP is equal to the concentration of each of the ions. Okay, so it does make the math a lot easier, and because we're dealing with very low concentrations, we're going to be doing something else when we have to minus or plus an X that is also going to make the math a little bit easier, so we're going to get to that in a minute. But just remember that KSP shouldn't have anything on the bottom. It's just going to be the two ions. This is a solubility product constant chart. You will always be given what you need in the problem or on a worksheet. You never have to memorize these. But these are just some of the ones that you... And I said you don't.
Oh.
Yes, you do. For those of you who didn't listen, I said you have to memorize. If you're on the video, you don't have to memorize.
1 times 10 to the negative.
Yeah. Only Daniel and Alex have to memorize because they're being smart Alex. Okay. All right, so write the equilibrium expression for these. And so we're just going to say this would be concentration of Ca plus 2, and then concentration of F minus raised to the 2. Why raised to the 2? Because of the coefficient. Okay? Because of the coefficient. And then that means that this one would be Ag plus squared, and then CrO4 minus, and then this one would be Ca plus 2, and then...
And these are brackets?
Yes, because they're concentration. A couple of you still missed that on the quiz. You put brackets around your pressure. Some of you just listed parentheses with the compound. You still had to put a P for pressure. So some of you missed that point.
I did that.
I don't know if you did that. Okay. Here's something that I'm going to caution you about 2 or 3 times during the lesson for this, because it's a mistake that consistently kids make. When you go to put the concentration in the brackets, or you go to put an X value in there, based on the way they break apart, you would put this as X, but you would put fluorine as 2X. Because it's, remember, when we dissociate something, it's double the concentration if there's a 2 in front of it. So really and truly, if we were to put X's in this value, we would put X, and we would do 2X and then squared on the outside. So that's going to be an important concept. Because of this 2, the fluorine concentration is going to be twice as much, because remember how things dissociate. And that is the most common mistake made in this unit, is that they don't do the 2x. They just put the thing, and then they get the answer wrong. So this one would be 2x, and then this one would be x, and then x and x, if you were putting in an unknown concentration there. Okay? I will say it again in a minute, because that is the most common mistake made every year. Okay? All right. So solubility expression for KSP, pretty straightforward, pretty easy. Okay, so determining the KSP in practice, they're measured by careful laboratory measurements, but we're going to be using mathematical, and the stoichiometry is going to be very important in these. You can never forget the stoichiometry. Okay, so here's an example of that. We have Lead chloride dissolves to a slight extent. If we find the lead ion concentration to be 1.62 times 10 to the negative second, what would the chloride's concentration be? So you would be 2x. So you'd have to multiply that by 2 because of the stoichiometry right here, because it's 2 to 1. So this is the lead, 2 plus, brackets, and then this is the chlorine. And then it's squared, so then we can calculate that Ksp value. Okay? You have to remember to double it and square it, basically. And that's what oftentimes, because this value would need to be 2x and then bracket squared. Okay? So don't forget about the stoichiometry. Okay? So here we have copper 1 bromide has a measured solubility. Sometimes we call this a molar solubility, so recognize that, of 2.1 times 10 to the negative 4. Calculate its Ksp value. So our Ksp is, so we know that copper 1 bromide is going to break apart into copper plus Br minus. So Ksp would look like Cu plus Br minus. So we would plug in that molar solubility or measured solubility, and it would be the same value since it's a 1-to-1 ratio. So our Ksp would be 4.0 times 10 to the negative 8.
KSB still doesn't have units.
Yeah, no, your K values, whether it's Ka, Kb, Ksp, Kc, Kp, none of them have values. When we get to acids and base, Ka and Kb is for acids and bases, equilibrium. Forgot the negative sign, sorry. Thought I wrote it. Okay? So let's do another one. Calculate the Ksp value for bismuth, which has a solubility of 1 times 10 to the negative 15. So this is one of those times where I want you to calculate it, and then we'll catch up. So y'all try that real quick. I'm going to pause the video. Y'all try it at home. All right, so it should look something like that. Okay, you have to remember to multiply the concentration by the stoichiometry and then square it, and then multiply the concentration on the sulfur as well. Okay, so when you have a that's a very, very small number. So this means it is, I mean, there's just barely any solubility there of this because it's a negative 73. The closer to a whole number that is, and the more soluble it is. Okay, so negative 73 means it's really, really not very soluble at all. Okay? Okay. Do what? Oh no, once it won't come back, I'm sorry. I have it on in my notes package. You can look at it later if you want. Yeah, unfortunately, once I go away, it doesn't come back. So estimating the salt solubility from a Ksp, so you can, like we said, that was a negative 73, so it's very, very insoluble, okay? But you can compare values to see what's going to be more soluble than the other one, but you have to be very careful with that. You can only do that if you have the same number of ions. So if I have a Ksp value for silver chloride, okay, I could compare it to silver bromide because they both have 2 ions. But I could not compare the Ksp values for lead 2 chloride to silver chloride because lead 2 chloride has 3 ions, whereas AgCl only has 2 ions. So if you're going to compare your Ksp values, you have to have the same number of ions. Okay, that's the only way you can do a direct correlation. If not, you have to do some calculations to figure it out. Okay, so just be careful about that. Okay, so here is the Ksp value for copper 2 iodate, and they give you the Ksp value. So calculate its solubility. Okay. So we're going to need to do a rice table here, right? So, okay. So, welcome to AP Chemistry, Mr. Gaffon. All right. So we're going to do our rice table. We have CuIO3. When it dissociates, it's going to give you Cu2 plus plus 2IO3, which is iodate. So there's our R for our rice table. This is going to be 0 throughout, so we can ignore it because solids do not appear in the rate law expression. So initially this is 0 and this is 0. So then at change we're going to have plus x, and this one's going to be plus 2x, right? So those are our equilibrium concentrations. So now we would have our Ksp value is times 10 to the negative 7 is equal to the x and 2x squared.
That's a different number. Oh, you're on exercise 3.
I am on exercise 3.
I was
Okay?
on the example above it.
Oh, yeah, sorry.
It's basically
There wasn't enough space there, so I just went,
Okay.
yeah, same concept. So then this becomes equals to 4x cubed. So by now you know how to do that math, right? Take the cube root.
yes.
Or, well, first of all, divide by 4. Yeah, sorry. First of all, divide by 4, and then you'll take the cube root. So you'll get that x is equal to 3.4 times 10 to the negative third moles per liter. So that would be its solubility.
Wait, that's.
Your trophy is like right.
Oh,
man.
my trash trophy's in the
Too much
way.
recycling, Miss Parker. Man.
I'm sorry.
You just love the planet too much.
I will move my fabulous trophy that I worked so hard for.
We're
Crushing cans. Okay. All right. Any questions on that? We're going to do another one. Well, actually, you know what I'm going to make you do the next one.
What? Do it on our own.
Do it on your own. No, actually,
That's what you were
the next one I can't make you do on your own because it's common ion. So that's different. This is where the math will become easier because we can do something. We're going to get to neglect something. Okay? So that's how you do that. All right? Any questions on that? This right here, I'm going to say it again. I said it once already, but this is important. This 2x. You have to put that 2x and then square it. Okay? If you don't do that, a lot of times people will square it because they're used to putting it raised to that, but because remember when this reaction dissociates, it dissociates and you get twice the amount of iodate that you do copper. Okay? So you got to remember to 2x and then also square it. Okay, so based on the Ksp value. Dang it. Okay. Solubility of common ions. Okay, so that's what happens if you've got the same ion coming from the same place or two different things. So in this case, we have calculate the solubility of calcium fluoride in a solution that is 0.025 molar sodium fluoride. So you already have some fluoride present, and you're going to add some more in the form of calcium fluoride. So what is that going to do to the solubility? Okay, and so again, we're going to do our Rice table. So we're going to say CaF2, reversible for forming Ca2 plus 2F minus. Okay, so there's our R, I, C, E. So our initial, of course we don't care about this, so we can just ignore it because it's a solid. Initially we have 0 calcium, but how much fluorine do we have?
Do we not know? Or
0.025 because it's coming from the sodium fluoride. So initially we have 0.025. So then we're going to plus x plus 2x. So at equilibrium, I didn't need that. I put the line in the wrong place, sorry. So at equilibrium we have x, and then we have 2x plus 0.025.
do we square?
Or the other way around. We actually want to do that the other way around, I'm sorry.
Do we square it or not?
Well, when we put it in the equilibrium expression, we do.
Yeah.
We actually want to do 0.025 plus 2x. Okay? So now we have our KSP was 4.0 times 10 to the 11 equals the x for calcium, and then 0.025 plus 2x squared. Okay? So here's where I'm going to tell you. We're dealing with small concentrations. 0.025 is a small concentration, but because the solubilities are so small, we get really, really small numbers. So we couldn't do it in the last unit, or the last just regular, because we're dealing with larger concentrations, larger changes. But oftentimes when we're dealing with KSP values, the X value is going to be so small that it's not going to make a difference. So we do something called neglect the X value. Yeah, you do. Okay, awesome. Okay, but you have to, what you have to do is you go ahead and, but you, if you're saying this in an AP test, you need to say neglect X. You need to tell them that I'm neglecting X because it's going to be so small. And then when we're done with the calculations, we're going to check to see if the X value we end up getting is within 5%. If it's less than 5% of the original concentration, then the assumption was valid. If you assume it and you get an X value that's greater than 5% of the original concentration, you got to go back and put X back in. I know that seemed confusing because it's the first time you see it, but you're going to love that we can neglect X because it makes our math way easier. Okay? So we're going to say, I'm going to do it in a different color. We're going to say assume X is negligible. Okay? So when we do that, our value becomes, back to red, 4.0 times 10 to the negative 11 is, you still have to keep your X for calcium because that's the only way we can get that. So we get X times 0.025 squared.
Whoa.
Isn't that a lot easier? So you do the math in your calculator and you get X is, we say this though because we neglected, we say this means approximately equal to 6.4 times 10 to the negative 8 moles per liter. And then we check, is that smaller than 5% of the original? And absolutely it is. So the valid assumption was that we could neglect X.
The original we're basing
The
on?
original is the 0.025.
Oh, okay.
Yeah, because that was the, so basically what it's saying is the concentration of fluorine, by adding the calcium fluoride, the concentration of fluorine is really not going to be affected by adding the calcium fluoride, but there will be a very small amount of calcium now dissolved.
Okay.
Okay? Now is where we ask questions because that might have been a little confusing.
So you only get rid of the X in the part where it's being added.
Where it's being added or subtracted. Yeah.
Because
Because the origin, so this is, the common ion here is fluorine, right? So by adding the calcium fluoride, it's going to be such a small amount that mathematically it's not going to change our fluorine amount, okay? It's like if you were a millionaire, $100 to you is not a big deal. But as a high school student, $100 is a bigger deal, right?
Yeah.
So to a millionaire, they can neglect $100 because they're not going to miss it, okay? But y'all can't because you probably don't have a lot of money like a millionaire, right? So there's a way to look at that. You're not going to affect the concentration of the fluorine by adding that small amount of calcium fluoride. But you do have to keep X in there because we've got to figure out what calcium is. All right? All right.
what are you checking at the end?
So you want to know if the value you get for X is less than 5% of the original concentration. I mean, we don't even need to do the math for that, do we? I know that a times 10 to the negative 8 is way less than 5% of a 0.02.
How do you have to calculate it sometimes?
If you got a larger X value, then yes. There are times when you neglect X and you go to check your 5% rule and it's, you go to check your 5% rule and it is greater than 5%, so you have to go in and then you just go back in and put X and solve it that. Yeah. Okay? All right. Shall we do another one? Shall we do another one?
Yeah.
Oh, yes, Frank, what's your question?
Okay, so the reason we neglect X is just to make the calculation easier, or is it?
Well, yes, the reason we neglect X is to...
Hey, should we get the door?
Hold on, let me pause the video.
Are you okay, sir?
If the doorbell rings again, can one of y'all get it since I'm in the middle of lecture? Thank you, Shimo. Okay, so the reason, Frank, the reason we neglected X is because X is, we're dealing with a concentration that's fairly large compared to our molar solubilities. So if we had, it would make no difference. Like if we kept X in there, still solve for it, when we subtracted or added, it would still be 0.025. because that's like that's like 7 zeros. So our concentration for fluoride would be 0.02500000006.
Yeah, but for Ksp, it was like 10 to the negative, like 3, then we would.
Then we would need to look at that. So my advice is, unless it's obvious that it's going to be a big change, is neglect X and then check the 5% rule at the end. Okay. If it is over 5% of the change, then just do it back, put it back in there and go. Yes, your question.
So I understand why we neglect X, but like why just the 2X in like in the concentration?
Oh, because remember, it's 0.025. Okay? If I added that X value to 0.025, it does not mathematically make a difference because we had the common ion of fluorine. But the only calcium we have is coming from what we added to it. So we have to calculate that X.
Okay, because we need to, I mean, I know why we need to find an X, but it's just confusing when we just get rid of that 2X. Okay, I get it.
Because the 2X is not going to be enough to make a difference on the original concentration. Again, we'll go back to if you have $1 million in your bank account and you add 100, you're not going to notice. But if you have $5.55 and you add 100, you're going to notice. Yeah. Okay. Okay. So now we have KSP and the reaction quotient. Okay. So same concept in the last unit about comparing. It's the same concept about the same concept of comparing Q to KSP or K. It's still going to do that, but now when we talk about shifts, we're not going to be talking about shifting left or shifting right. We're going to talk about will it precipitate or will it not precipitate. Okay? It still is the left or right. Okay? But now we're saying, instead of saying shift left, we would say it would form a precipitant, or shift right, it would not form a precipitant.
Wait, which one's which?
Well, I'm fixing to tell you.
Oh, so only like the supersaturated.
Precipitate forms when it's supersaturated.